So,
okay, Valeria, whenever you're ready.
We are ready. So let's go. I was exactly going to say, good morning, good afternoon, good evening. We are very happy today to have a slightly different Topos seminar, Topos Institute seminar, because we are very, very proud to have Professor Zoé Christoff from the University of Groningen talking to us today about the logic of social influence in networks. I thought I should say a few words about Zoé before we start. So Zoé is assistant professor in cognitive AI and the Rosalind Franklin Fellow at the University of Groningen. And she previously worked at the Department of Philosophy of the University of Bayreuth. I mispronounced that for a fact, and the Department of Computer Science at the University of Liverpool. She obtained her PhD in logic at the University of Amsterdam with a dissertation on dynamic logics of networks and information flow and the spread of opinion. And her foundational research aims to uncover the logical laws of collective opinion formation and collective decision-making. To do so, she combines tools from logic, formal epistemology, social network theory, and social choice theory. And it's a great pleasure to have you with us, so take it away.
Thank you so much, Valeria, and thank you to the entire Topos team for inviting me. I'm very honored to be part of this seminar. I've looked a little bit at your institute, and I'm intrigued, to say the least, by the range of topics covered by the people who are part of the institute. So what I decided to do for today was to give some sort of a general tour of the topic of logic of social influence in networks. Also because I assume that people who will join here are familiar with different tools, and it would take me the whole hour to just present one paper. So I thought, let's go for the full big picture story in hopes that I convince you there's some reason to do logic for social networks. And so let me start. Oh, let me not start this way. Okay. That work. Okay, so I'm interested in the foundations of social influence, and that means on the one hand, in understanding how human agents reason and behave in the real world. Though this is some empirical component, although I'm not a social scientist, I'm interested in what real phenomena have been observed among real people. I'm also interested in understanding how ideally rational agents would behave on a purely theoretical level. And throughout the talk, I will use those different little figures to keep in mind those ideas. And of course, I'm interested in the logical side of this. The big picture I have in mind that I would like you to keep in mind for the entire story of this talk is the following. I'm interested in understanding the relationship between what happens at the individual level in terms of behavior or individual rationality and on the collective level. So on the behavior of group or the collective rationality of groups, no matter what that means. That means different things in different contexts. But overall, all those questions are somehow related. So I'm interested in understanding when individuals are smart in some sense, whether the groups are also smart or not. Okay. So a first example of the type of question I'm looking at, obviously this is not my work, this is work from Schelling from the 70s, but it's to give an example of a treatment of a question that fits into this big picture. So Schelling's segregation model, which you might all know, but for just, I will recall it here in 1 minute, is a very simple model of segregation, looking at very segregated cities, typically in the US, but not only. People might have the impression that individuals just don't want to live in mixed neighborhoods. And Schelling's model actually showed that this is not necessarily the case. The model works as follows. You have two different types of agents here, blue squares and yellow triangles. And you assume that those agents just are not very comfortable being in a very, very small minority. So they want to have among their neighbors some agents who look like them. And if those agents are below that threshold of comfort, they will move to another spot on the grid. And if you assume, for instance, that the threshold is 1/3, so you can run the model making all agents uncomfortable or unhappy if they have less than 1/3 of their neighbors on the grid that are of their type. Then from this relatively small bias, you end up in a situation that is entirely segregated, as you can see on the right. And so the lesson from this model is that a small individual preference, even if agent would overall prefer to be in a more mixed neighborhood than what they are actually living in, would still result in a very strong segregation. So what does the model show with respect to the picture I was looking at? It shows that a strong conformity bias is not necessarily leading to strong segregation on the collective level. And actually the model also shows that the other way around, the other implication is also not there. Okay, so this is just so that you can keep in mind throughout the whole story the type of question I have in mind. And of course, this is very schematic how I present it, but the model is sufficiently simple that I think it gives an idea of how to look at those things in a simplified way and still learn something really important about what is modeled. Okay. So I said I'm interested in how real people actually behave. So I want to give a very small introduction in the type of phenomena I'm talking about. So you take a bunch of humans and you just look how they behave. You just look at how they behave. Okay, so first, the question, of course, is do they collectively behave in a way that seems smart or whether it doesn't seem smart? And in 1907, Francis Galton was pretty decided into showing that masses are not very good at deciding on important issues and that one should only listen to experts. And he actually used the guesses from the audience, so a group of people going to a fair where they could participate into a competition of guessing the weight of a cow that was in the fair. And his goal was to show that masses are really bad at this, that only the experts would have the right answer or close to the right answer. And to his own surprise, he was actually wrong. So the crowd collectively, if you would take the average of the guesses of the crowd, I think around 700 people, the average was 1 pound off the real answer, much better than all the experts that were also involved. And so Galton concluded, oh, maybe the masses aren't that bad. Maybe there is something to this democracy idea. Okay, that's historically a cool story also. A very short article, I recommend looking at it if you need a break from more formal things. Okay, since then, this has been empirically repeated many times. If we were a large audience, I could show you a jar of jelly bean and ask you guess how many jelly beans are in the jar and take the average of your guesses and probably be very close to the right answer. So this is not a unique, it's not an accidental finding. It's been replicated many times. And since then, this has been labeled as the wisdom of the crowd. So it looks like the larger the group, the wiser, really. And beyond the empirical side, there is already a result that was known at the time, that is the Condorcet-Jury theorem, that says that if you have a group of jurors, a population, a crowd that needs to decide between two possible answers, if the probability of each of them is whatsoever better than random, so they are just better than 50-50, then you can show that when the group size becomes larger, tends to infinity, the probability that the majority gets the right answer tends to 1. So this is the limit case of what we were describing as like the larger the crowd, the wiser. And now, of course, I started by talking about real humans, but this has nothing to do with real humans. This is just a mathematical theorem. So you can take away those humans and say, well, this is just a limit of whatever any group of agents can do collectively. Okay. So this still holds, of course. So without social influence, now we were talking, crucially, we were only talking about independent guesses of those agents. And without social influence, it looks like large crowds are wiser. So we have this effect that independent individuals makes for a wise crowd. Now, what we want to know, of course, is what happens with social influence, because in practice, we don't have independent guesses. Yeah, I'd argue you almost never have independent guesses. So the question is, what happens when you take social influence into account and still try to model in a formal way what happened at the collective level? Okay, so sometimes things go wrong, as we know. Sometimes individuals just lead each other in the wrong direction, and this is proof by cartoon. Just a normal day at the nation's most important financial institution. The first person say, I've got a stock here that could really excel. The second one here is really excel. The third one excel, and all the other one here sell, 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 and it's a general panic, or the other way around. Obviously the cartoon is a little bit foolish, but it's you can easily imagine situations where this actually would happen. So then you wonder, okay, maybe groups aren't so wise when their choices or their decisions are correlated. Stop working. Okay. So I'm particularly interested in correlated behavior and collective failures. And there are many examples in the social psychology literature, such as informational cascades, pluralistic ignorance, bystander effect, polarization, and many more. Maybe those are the most famous. And I'll say a little bit about informational cascade and pluralistic ignorance. So the first one, pluralistic ignorance, is typically described as a situation where the majority of group members privately rejects a norm, but assumes incorrectly that most others accept it. The typical, the most famous example of that is actually Anderson's fairy tale, The Emperor's New Clothes, where the emperor is parading in his new clothes, supposedly invisible to those who are unfit for their position, stupid or incompetent. And nobody dares to say anything, to say, oh, but the emperor is naked, until a small child actually just says it out loud. And then everybody realizes that probably they are not all stupid, incompetent or unfit for their position, but the emperor is actually naked. And beyond the fairy tale, this is a phenomenon that has been observed by social scientists and social psychologists, also repeatedly and sufficiently that we know this is something that actually happens relatively easily. So the examples where we observe pluralistic ignorance are, for instance, classroom situation where I'm sure you've all experienced if you ask students after a difficult lecture if there's one of them who didn't understand something and that they should speak up now, this typically ends up in silence. And probably if one of them is hesitant to ask, they wonder, am I the only one who didn't understand anything? And I'm the only idiot in the class. And so this remains in a stable state until somebody speaks up and kind of breaks the illusion. Another example that is quite famous is the college drinking norms in some campuses in the US, where researchers asked the students to give on a scale how comfortable they were with some heavy drinking norms in their college and how comfortable they thought other students were with them. And they pretty much all were less comfortable than what they thought that all the others were. And this results in heavy drinking norms perpetuating for generations, even though most students might not like them. Some might like them. There's a lot of research actually on how they might cope with this. So this is quite interesting, but it's of course beyond my own point. And another example is segregation norms, where there are some studies documenting how in some neighborhoods, parents, for instance, were totally fine with their children playing with children who had a different skin color, but they thought that the neighbors will find this wrong. So therefore, they wouldn't allow it, for instance. And you can see how then unpopular norms that everybody hates might actually stay in place for a very long time. So to model situations like this, like pluralistic ignorance, we need to take into account not only the actual opinion of agent, their private opinion, but also their behavior or what they actually show to the others around. And an example, again, by cartoon, would be a committee that has to vote on something and they're all against the motion, but they all vote in favor and possibly vote in favor because the first one does so, or they just don't dare to be sincere. And if only they would know what the other are thinking, they would just all agree on the opposite answer. So this is collectively not optimal. This is the point. Okay. The second example is informational cascades. And this is typically a situation where agents disregard their own private information to follow the choice of some preceding agents, and where all remaining agents in a sequence pick the same option, even if they have diverging private evidence. And so it looks like an imitation effect, and this can lead an entire community to make the worst possible choice. This looks a little bit like our cartoon earlier. But again, this is relatively easy to observe. And the classic example here is the choice of a restaurant. So you have two restaurants you have to choose from, and they are just next to each other. And you start, those are the two restaurants, A and B. And you start by doing your research, and you find a lot of information saying that restaurant A is supposed to be better. So you decide to go to restaurant A, but when you get in front of restaurant A, you're pretty much the only one there. And then you see that restaurant B has a long queue outside and is completely packed. And then you start thinking, but those agents must have good reason to want to go to restaurant B. And therefore you go also to restaurant B, who has even more success. And you can see how this grows through time. Okay, so this is the simple example. And then we can ask, are those informational cascades just mindless imitation effect? Is it really just repeating the mistake of a first agent? And then everybody repeats it because one person, so in this case, the fourth agent speaking, makes a mistake, just misunderstands, and then everybody repeats that very mistake, that very mistake. So sometimes informational cascades have been seen in this way. Okay. And now the researchers working on this type of phenomena, who are typically not logicians or formal researchers like me, they are likely to be interested in the following question. What are the conditions for such a phenomenon to happen? Where is the individual error leading to such collective failure? And can we prevent it? Can we correct it? Okay, my question is, can logic help with any of these? Well, I hope I can convince you that it can by showing a first example, which is a paper we did together with Alexandru Baltag, Jens Ulrik Hansen, and Sonja Smets about modeling informational cascades using dynamic epistemic logic. And to do that, I first need to introduce the case we model. So this is, again, a classic simple example of an informational cascade. That is, among other places, presented in the network RAD and market textbook that is mentioned here. And so the idea is that you have a group of agents entering a room. In the room is an urn that is opaque, so you cannot see the marbles that are inside. And nobody knows whether the urn contains more white marbles or more black marbles. We know, everybody knows, that it contains 3 marbles. So it could be that it contains 2 white ones, or it could be that it contains 2 black ones. Now the setup is the following. Each agent successively goes and look, say, behind the curtain, goes, picks a marble from the urn, looks at it, looks at the color, puts it back, and then comes back in front of everybody and writes their guess on the blackboard for everybody to see. So the observation is private, the guess is shared publicly. And so their guess is just, is it the urn W that contains more white, or is it the urn UB that contains more black marbles? And the goal is for each agent themselves to win, to guess which one is the right urn. So if they guess the correct urn, they win a chocolate. So That's just what I've already explained. So the first agent comes in and picks a marble. If she observes a white marble, she will guess for the left urn. If she observes a black one, she will guess for the other one for obvious probabilistic reasons. Okay. Then she picks a white marble and therefore comes back in the room and writes the guess UW on the blackboard for all the other agents to see. Sorry, I skipped the second one. Okay. So the second agent in the sequence will have seen already the guess of the first agent, UW. So this agent already knows that the previous agent has seen a white marble because this is the only explanation for her guess. So she knows already one white marble has been observed, and then she goes herself, picks up the marble. Say now she sees again, she observes a white marble again. Well, obviously, she will also guess for UW. Now, the interesting part starts now. When the third agent in the sequence comes to observe their own marble, they can already see two previous guesses in favor of the urn with more white marble. And therefore, they know that the two first agents have seen a white marble. Now, when they observe a white marble, obviously, they will also guess in favor of the same urn. But if they see a black marble, but they still know that two white marbles were seen previously, so they will also guess for the urn with more white marbles. And here you can see that this means that the observation of this third agent doesn't matter. No matter what they see, they have to guess for the same urn as the two previous agents. And now the fourth agent will be in exactly the same situation and all the following agents as well, which means that if all the following agents see 55 black marbles, they'll still all guess for the left urn. Okay. It seems like this is the rational thing to do for each of them if they are just trying to maximize their chance of winning a chocolate. Collectively, this is bad, right? It means that almost everybody in the group will lose, but individually, this is all they can do. Now, sometimes when we present, I'm not sure how this audience feel about this case, but sometimes when presenting this example, they are typically students who disagree that this will actually happen. So we have the feeling that if agents are aware of how things work, they should realize that they are in such a cascade, and therefore they should guess differently. So what if agents were really, really, really smart and they could somehow escape the informational cascade? So to answer this, it's easy to answer this objection by just saying, look, it's just probabilities. But then people say, yeah, but if you can reason about how other people reason about probabilities, maybe there's something else you can do. And what we did in the papers show that actually there is nothing else you can do by including not only the probabilistic reasoning of the agent in the model, so this is the probabilistic version of dynamic epistemic logic, but also modeling all the higher order knowledge from each of the agents. So this is up to infinite levels. This is the advantage of using epistemic logic. So to do this, we just model, so I will not go into the detail of dynamic epistemic logic because I'm not sure how familiar the audience is with this, but it's just to give you a feeling of how what we do in the paper. So we just represent the same cascade with an initial epistemic model. That's just a situation where all agents assign the same odds to both urn being in the room, or to either of the two urn being in the room. And then we can model the observation of a first marble as an action model that includes the probabilities for each of the two urn being the case, given what color of marble has been observed. And then we do a product update between the initial epistemic situation and the action model. And we get new odds for each of the four possibilities for each of the agents. Now, this is just a new epistemic model showing what agents know, what they don't know, and what odds they assign to each possible situation. So that is which one is the real urn and what color of marble has the first agent seen, W for white and B for black. This is what they know after the first observation. And the important part is that once the first agent comes and announces her guess, then the model shrinks to a situation where they all, again, where they all know the same thing, and this is the resulting model. So we can just continue as such, apply the same action model to this model, and see what happens. This is after the second agent announces her guess, and this is after the third observation. Now the important bit is, I cannot point. Okay, the important bit is what is at the bottom of the slide. That just means that agent 3 assigns odds greater to the earned being the earned on the left than the one on the right. And this thing is now common knowledge in this model. So what does it mean? It means that when agent 3 will write her guess on the board for everyone to see, it will not change anything because it doesn't contain any information. And so what we can do is basically write a proof on the sequence of models that we obtain to say, from this point on, all of these models look the same. There are more states because each observation might be different. So you need to multiply the number of states, but they all look the same from a bird view. And you can just prove that this will never change. And those models include everything one can think of, including if you want to model ideal agents with perfect probability computation and perfect higher order reasoning. Okay, conclusion, this is still perfectly rational. So yes, rational individual will lead the group to a catastrophic outcome in many cases. We also discuss shortly in the paper, this is still in less many cases than in the case that they will lead each other to the right answer, but not, it's not that reliable, right? There's a very high probability of leading everybody to the wrong answer. Okay. So obviously this is not optimal. Okay. So what, going back to my big picture, what does this dynamic epistemic logic model really show? It just shows that having a collective failure doesn't rely on an individual reasoning error, like some people sometimes seem to assume. Okay. So individual rationality can very well lead to collective disaster. And in this case, actually, individual irrationality, so an agent making a mistake somewhere, would actually help the group collectively. And that's, again, this is true for any type of agent. This is somehow modeling the limits of what is possible. Okay, now let's go to social networks, because this long introduction was just to talk about what happens when you don't have influence, what happens when you do have influence and sequential information. And the point, of course, is to get to networks. So to do that, I also first need to do a small detour by via simple diffusion models in social networks. So you can think of this as a crash course in diffusion models. And for this, I will use some slides designed by Pavel Nomov for a course we gave at SE on social networks. So you will see some very exciting pictures. Those are all Pavel's creation. Okay, so the first type of model that is used everywhere, that if you open a textbook on social network, probably one of the first chapter will be threshold model. So a threshold model is a network structure. So you have here a set of green nodes and some relations between them, which should correspond to any type of influenceability relations between the agent. And you assume that they have a threshold, all agents the same threshold, which is just a measure of how influenceable they are. So you start with agent having a color that can be any agent attribute, a trend, an opinion, behavior, a product they would buy. And then to update the model, you apply the following rule that for each agent, they will adopt, say, the new colors, because that's what is easiest to show on slides. If the ratio of her neighbors who already have it is at least the threshold theta. So in the example here, we'll just use a threshold of a half, and we'll just start first with some seed agent who will have adopted the new trend or color for absolutely for reasons that are absolutely separate from social influence. So they are paid by some marketing people to be the first to adopt it. Okay, those are the agents, and they are purple. Okay, so if those three agents adopt first, then they will influence this central agent, who in turn will influence the two other agents. And this is all there is to threshold models. This also captures coordination game in networks. So it looks extremely simple, but there is perhaps more rationality behind it than might seem at first sight. In some cases, we have a complete cascade. So we have a new color, the purple one, that will spread to the entire network. So for instance, if you convince those two agents to be the initial adopters or the seeds, they will convince in turn all other agents in the network. Okay, and in force that you have a complete cascade. This is not always the case, and if we want to know when is this the case, there is a well-known theorem saying all nodes will eventually be infected or adopt the new color if and only if among those who were not infected, there is no cluster of density higher than 1 minus the threshold. So this just means if there is a threshold over half, there isn't a group who has at least a half of their friends or neighbors or influencer within the same group where they all were not part of the seed. So this is just a group that you cannot penetrate by social influence. Okay. The second type of model that you would see on the social network diffusion 101 is probably the Decode model. So this is a little bit more fine-grained. You still have agents, the three nodes are agents, and then you have arrows for who influences who. And those are weighted arrows. So for instance, if you look at agent 1, that's the purple one, agent 1 is influenced for 1/3 by agent 2, 1/3 by agent 3, and 1/3 by himself. And the network together with the influence weight is represented in the matrix T. And then the model works by, I should also say that each agent has an initial opinion that is also between 0 and 1. So this is more fine-grained than my two colors initially, but you can, for instance, start with the second matrix 1, 0, 0 is just the initial colors or extreme opinions of my agent 1, 2, 3. And then you can multiply the influence matrix by the opinion matrix and by what we know about properties of the limit of matrix multiplication, we can calculate what the opinions will converge to in the long run. So this is a very famous model, and usually we are interested in when do those things stabilize, when do they actually converge, and the result is a little bit harder to state than the preceding one, is that it converges and only if in each strongly connected closed set, so this is each group of agents that all have a path between any two of them, and do not have influencers from outside the set, the greatest common divisor of all cycles is equal to 1. Okay. So I had an example of this, apparently I split it. So if you have a network with two cycles, one of size 3 and one of size 4 that are intertwined, obviously they will not be able to synchronize in order to oscillate. So at some point, the dynamics has to break down and everything will stabilize. But if you have a cycle of 2 inside of cycle of 4, they might actually oscillate at the right moment and they might just continue forever. So this was just to give you an idea of the type of question that people who talk about those models are typically interested in. So typically they look at one class of networks for one specific application and one class of update rules, and they ask which diffusion states are reachable from which. For instance, can we reach a consensus or not? Which diffusion process stabilize and what graphs guarantee stabilization? And I already gave you 2 results about those 2 types of models that answer some of those questions. Okay. Now again, I want to ask, can logic help with any of these? And I hope to show that it can by showing an example of logical models of influence in networks. So this is more, for the previous section, I gave you one paper for informational cascade. This is a much wider topic. So behind it is some sort of a naive idea that those processes are all, if you look at it from a logician perspective, they're all basically a graph, a network here on the left, with agents being on of different color or having different attributes, satisfying different propositions. And you need a way to represent an update rule, which I drew in as a very simplistic automaton on the right side. So on the right side, I mean to say that, say you have an agent who is either purple or not purple, then you need some condition phi to go from purple to not purple, and some condition psi to go from not purple to purple. And this is pretty much what your update rule gives you. We apply the same rule on all the agents at the same time iteratively. And so far, those models were doing something like that. Of course, there are many questions. Is this really an automaton? Not really. Where do the phi and psi come from? So you can see this is a very big class of questions, actually. But we have to start somewhere. Somehow I have to click back. Yeah, okay. We have to start somewhere. So we can start with the smallest possible example of such thing, which is again 2 states or 2 colors. So just P or not P. And for the condition phi and psi, there is one minimal assumption we can make, is that an agent who is not influenced into changing state when all of its neighbors are in a different state is just an agent that will never change his mind. So we are not really interested in those. We are interested in the limit of when does something happen. It should happen at least when everybody is against you, right? If everybody has the opposite opinion, you should switch. Okay. So the minimal example in this case is just a unanimity-based rule. That would mean if you were purple and all the agents around you, all your network neighbors or influencers are not purple, then you will stop being purple, because this is a scary place to be. If you were not purple and all your network neighbors were purple, then you'll be like, I'm happy to be purple. Okay. Then we might wonder what happens if we just look at this, purely this very simple object. This is just a threshold diffusion model where agents can also unadopt, contrary to what I just introduced before. So there is this symmetry that is in the way the rule is defined with a unanimity threshold. So if you have those 2 agents as initial adopters like before, they will just turn back to being green very quickly. So nothing will happen. Okay, so you would need much more to, it's actually pretty much impossible to start with those 2 and convince anybody. Okay. Now we can wonder what is the, when does this type of process stabilize? Okay, so now I was assuming that my graphs are just symmetric. I didn't say anything about this before, but you could wonder, right? Here I just have some type of friendship relationship. And in some cases, like in the model that you are looking at now, you have 3 purple agents, and this will be sufficient to turn a 4th one, and this will be sufficient to turn everybody. Even though the first, one of the first purple agent became green in the meantime, it had enough support in the rest of the population to be able to become purple again later on. Okay. This is one example of a complete cascade with some agent dropping and coming back to the purple. Okay. Now there are also cases where we don't have enough seed agents, so those 2 purple agents alone will just go back to being green again. And both situations are stable, but this is not always the case. So of course, because I'm inspired by those convergence results on classic models from network theory, I was just curious, so when does this stabilize? And in this particular limit case, it's actually very easy to observe that the only case that oscillates are of this type. And before we were talking about the lengths of the cycles in networks, and this is again a case of forbidden cycle lengths. So with this update rules and symmetric irreflexive networks like we've been looking at, the cases that will oscillate are only the proper two colorings of the graphs. That means that we can say something about the graphs themselves. We can say that a graph that is not two colorable will always stabilize no matter the distribution of colors on it. So this is the third example on the right. No matter how many green and purples you put there, you will end up in a stable situation. But if you have a graph that you can properly two color, then there will be those proper two coloring, which will oscillate forever. This is at the same time a very simple observation. And at the same time, it keeps coming back all the time. So I thought it was worth building the story on this. So people actually doing logic for social networks before me, such as Finegrained, Jeremy Seligman, and Patrick Gérard, were interested in modeling slightly more interesting agents. So they had agents who could, for instance, believe that P, those are the green ones, believe that not P, those are the green ones, believe that P, purple ones, or be undecided between the two. And again, they had a sort of an automaton to explain what are the conditions for agent to change. And exactly like I introduced now, they assume that if everybody is against you, you will change your mind. There's no doubt. But in cases where only somebody is against you and somebody agrees, you will not, for instance. And there you have to make some choices that are maybe harder to justify than what I started with by just saying, okay, limit case, if we want to see influence, we need agents that are influenceable, at least in some cases. So if they are not influenced by the unanimity, they'll never be influenced. So they start with this idea of unanimity, but they add more fine-grained things. And their starting point was not mine. It was just modeling belief change in social networks from scratch. Looking at this model, interestingly, the only case that oscillates is again the proper two coloring of the graph. Now you might think, but we had three states, we had three different colors. Yeah, but it doesn't matter. So this comes back again and again and again, because it is an actual limit of those processes. So in their setting, any two agents, any two neighbors of the same color will be stable. So that already tells you, okay, so a two coloring is already avoiding that. A proper two coloring is already avoiding that. And any agent who is undecided in the setup is somehow sufficient for things to stabilize. So that means, again, the only situation that won't stabilize are those, even though that was not their starting point or their goal, and they don't mention that because this is irrelevant to their what they wanted to do with it. This was not their point. So, okay. But from my perspective, I thought, oh, this is interesting. Somehow it's still there. There are more theorems about diffusion stabilization from the perspective of social choice theory and in particular judgment aggregation. So people in judgment aggregation have been doing the same thing, but with different tools. So they modeled opinion diffusion as parallel iterated aggregation. So an agent just aggregates the opinion of all the influencers at each step iteratively. Of course, they ask slightly different questions. They want to ask questions about convergence for classes of voting rules or aggregation procedures that respect certain axioms, like in the typical social choice theoretic approach. But actually, what they look at are threshold rules and a similar type of dynamics where everybody updates their opinion at the same time in the same way. Okay, the slight differences are always in whether in one context it makes sense to have those symmetric irreflexive graphs, like if you want to model Facebook relationship, that makes sense. But in other cases, it makes sense that an agent takes into account their own current opinion, and then you do need some reflexive arrows, possibly with different weights than the weight from other people around you, and so on. So there are a lot of subtleties you can plug into those models, and they all matter for stabilization result, of course. So Umberto Grandi, Emiliano Lorini, and Laurent Perussel have in their paper Propositional Opinion Diffusion some results about this. because they don't look specifically at the limit case, those results are much harder to get. And they have them for very restricted classes of networks, like classes that networks, for instance, where cycles are never sharing a node, or you can basically reduce those as some complex chains. And so those questions in general are really hard to solve, and nobody has general answers about any of them, which I also find quite interesting. Okay, now we had agents with 3 possible states or 3 possible colors. I'm looking at the time because I'm very slow. So what if we want even more fine-grained agents? We had this example, right, where people do not express sincerely their private opinions, but where they say the opposite. And then if we want to model those cases, we need more than 3 states. We need to combine the inner state or private state of opinion of the agents, so they all privately believe that not P, they're all against the motion, but they all express a belief in P. And so if you do that, then of course you have 9 states of the agent, and then it's much harder to draw a simplified automaton and make sense of what is the right condition. How should they change their opinion? Should they change the private one, the expressed one? So we started by wanting to model what happens for pluralistic ignorance. So this situation where everybody believes something, but believes that the other people believe the opposite of it. And in which case we thought social influence is what forces you to express a specific opinion. It doesn't make you change your opinion. If you think segregation norms are bad, you probably didn't change your opinion on that. You just changed your behavior. You just changed what you express. So we wanted to model this specifically. And then we had to draw different types of agents. This is only one of them, one possibility, where we just decide on the most right column is just what the agent will express next. And this depends on the inner state of the agent, what they really believe, and what all other agents around them are expressing right now. So the case I circled with purple color is just the case again where if an agent only has neighbors who all express a belief that phi, so we're all in favor of something, then you yourself will also express a belief in phi. So this is again our limit case. If everybody expresses something, you will have to align. This is included in that table, but for the other cases, there are actually 2 of those, yes. For the other cases, we have to make some choices. When people disagree around you, does it make you doubt? You know, this kind of question. Those you have to choose, and you need good reason for that. And we are not very good as logicians to decide what are the good reasons. So we just said, oh, there are all these types of agents, just pick the one you want. But what they have in common is this limit, unanimity facing limit. You can drop that. You can have agents who are antisocial, and they will, when everybody opposes, they will adopt something. That's, of course, you can define those, but we were interested in social influence as some type of conformity pressure. Okay. This in turn helped us, so we modeled this type of agent, and we realized that if we have a state of pluralistic ignorance in a social network, so a situation where everybody believes something but believes that everybody else believes the opposite, we wanted to see when you turn one agent, so you just make one agent saying, hey, but the emperor is naked. When is this sufficient to reach a situation where all agents in the network are now sincerely expressing their opinion? So when can you break those unpopular norms, pretty much? And what we found out for this type of agent, which we were not looking for that specifically at all, is that this happens if and only if there is a cycle in the network of odd lengths again. So this is only possible if your graph is not properly two-colorable. And well, in a way, it's not surprising because we still have this built-in unanimity change. But this is not the only thing we have. We have many, many other things built in now. And this is still what we get when we look for results about when does one specific social phenomenon resolve in social network. Okay, now you can say, okay, all those models were very much ad hoc for one phenomenon or one type of agent. what if you want to model, age, gender, hair color, smartphone brand of the agent, and whatever you want to combine that you can combine. But also, fine, we'll make a general framework when you can model agents with as many layers as you want. And for each of those layers can take as many values as you want. And then on those, as long as you can define an update rule, then you have a logic for it, which also means that, yes?
Zoe, you got to the end of your time officially.
Oh, okay. I'll hurry. Thank you. I'll anyway skip the last part to make sure we can finish, and I'll still try to go through the main conclusion. Okay, so we have this general setup. This is together with Zoé Christoff, logic for diffusion in social networks. So pretty much whatever you can define that depend on the state of your neighbors, you can plug into that logic. Okay. Now, there is one last type of modeling my co-authors and I have done so far, is combining epistemic consideration with network directions. And in the paper with Alexander Baltag, Rasmus Rensvik, and Sonja Smets, we used dynamic epistemic logic of threshold diffusion. So we modeled how the agent adopt in a network, again, how they change color, but also what they know about the network structure and what they know about the state of other agents. And what we wanted to do was model different diffusion policy. The first one was just the standard threshold model policies where an agent adopts whenever enough of their neighbors have adopted. And you can think of those are agents automatically absorbing color. They're just permeable, they're like bacteria. And then we want to say, but this doesn't represent, the behavior of rational agents like people or reasonably smart agents, like people who actually can reason about what the others know and so on. So we thought, okay, so maybe the more reasonable policy is that when you don't know what your neighbors are doing, you shouldn't be influenced, at least. So when you would adopt only when you know that enough of your neighbors have adopted. So we just plugged in that epistemic component in the policy. Okay, so it can happen that you're not influenced because you don't know that your neighbors are of a different color. So then we thought, okay, but those agents are a little bit weird, the moderately smart one, because they might know that many other agents further in the network have been already influenced, and they might know that this is sufficient for them to be influenced later. So why don't they already change color? If the goal, as is often claimed, is to model coordination between agents on network, then if they are smart, that's what they should do. They should anticipate and already change. So we modeled those type of maximally smart agents again, that adopt using all the information they have in the network. And the interesting conclusion is that those are not very different because, again, from a distance, the dynamics is the same. What changes is the speed, but the fixed points you reach are always the same. So that means that people who design those models for threshold diffusion, and we also know that those correspond to rational, to the best response for coordination games on network. So this is not an accident. This is already rational behavior. So those bacteria are actually very smart. And with or without modeling all the information you can take into account, you will reach the same fixed points. Okay, so some people doubt that very simple model of diffusion in social network makes sense. Turns out they match incredible behavior change, like or attribute change, such as obesity or even sometimes suicide waves. Okay, so again, a little bit as for the informational cascade here, including in the model, everything you can include about the knowledge of the agent allows you to make this type of conclusion with a certain strength that otherwise I can just, of course, the initial bacteria model is great, but now I can say more. Okay. So this is my very short conclusion. I have presented 3 examples of insight from logical perspective. I have shown that informational cascades are inescapable for agents with unbounded higher order rationality using the probabilistic bell. I have shown, I've discussed the relation between network structure and diffusion dynamics and possibly stabilization results using different types of logic, modal, hybrid, fixed points. And I have shown how we can obtain insight on the behavior of very smart agents, how this might not differ so much from the bacteria-like agent using the diffusion epistemic logic. Now, this is not at all there is to say about this topic, even though this is almost all the time there is. There is by now, because this was a story, through a few papers. By now, there is an increasing number of papers from logicians on social network phenomena. There are several capturing directly what happens in the long run instead of capturing the step-by-step dynamics. Just why not have a logic that talks directly about the ability of a set of agents to influence another set? This is what we did with Pavel Nomov in a different paper, and in another paper with Thomas Agotnes, where we use coalition logic to reason about the abilities of sets of agents in networks. There is more, there are papers about how the network structure changes, how network tends towards structural balance. This is quite a popular topic among logicians, and how links in the network tend to be created based on agents who are similar, so based on homophily. This is typically the work of Sonia Smets and Fernando Velasquez. There are several papers, I only mentioned one. And this was the part I'm gonna skip. So this was the part about my current Veni project. If I manage to, scroll faster, I will just get to my end slides. Perfect. Thank you. I'm sorry for being a bit long.
I'm sorry to pushing you like this, but
no, this is great. My plan was to skip the last section unless I was magically very quick. So.
No, thanks so much. I think it was exactly the kind of talk that I wanted to hear, kind of giving the big picture, the reasons and how one thinks about that in a logical way, and it was great.
Because it's always easier to give a talk, a research talk with including all the details and definition and theorem. It's always safer than this big picture trajectory. So I'm glad if you think it fits the venue.
Thank you. Let's kind of go for some questions. I think I can see Tim's hand up there and Brendan's, so kind of go on, Tim.
Hey, thanks. So first of all, thanks. That talk was super interesting. It was really good. I don't know anything about this stuff, and I followed it. It was beautiful. So my question was kind of like, is there any, so some of the results you gave about like this thing about like coprimality and coloring theorems are like very dependent on like having a fixed number of nodes in your network. And I'm guessing it's a super difficult problem, but has there been any study on like small perturbations in terms of like, you might have a stable thing, then you just add one node and this can fully change the entire networks? Like, is there anything that logic can say about this kind of analytic phenomenon, I
want to say not yet, because so people have started by looking at this opinion change or attributes diffusion. So just keeping the same network fixed and changing the state of the nodes. And then they started looking, okay, let's not care about the state of the nodes so much or how they change, but let's care about when new links should be added and when links should be deleted. And now there are some barely submitted papers trying to combine those two. But it's still typically not in a small perturbation kind of way, but saying, okay, if you add links when agents are sufficiently similar, but at the same time they are influencing each other, and you update iteratively with something that combines both aspects, what do you get? So I think because we have been now, until now, focused on the things we know how to iterate, we have focused mainly on the uniform thing. At least there are some papers where threshold models can easily be generalized with different thresholds or different weights in the influence rules. But typically, logicians will not so easily start modeling things, saying, "Okay, if you add a node that, but why not? I mean, you could really." So.
Okay, thanks. That's great. Thank you.
Go on, Brendan, please.
Thanks, Valeria. Thanks, Zoe. That was a really, really lovely talk. I just want to echo my appreciation as well.
Thank you.
I found it fascinating and I learned a lot. I have a question in something similar to Tim's, just asking about future work, but in a different direction. It seems like many of these models are about individual agents or nodes have beliefs and they can make them transparent, and then other agents, whether it be through a social network or not, can pick up on the transparency of those beliefs and adjust their beliefs. One thing we think a lot about at Topos is communication, both from like a structured information, sort of formal mathematical perspective, and also from an informal perspective in terms of working together. And so a simple sort of notion of communication is just being able to ask like questions of one another. Do you know whether there have been models or are there models that have built in sort of very simple notions of communication and can show things like, I'd be interested in results, like if there is this simple ability to ask questions of one another, then we don't get information cascades and suboptimal outcomes like group dynamics, or sometimes if the notion is too limited, then we still do.
Not exactly in the way you described it, but there is previous work on, for instance, gossip spreading in network, which was something like two agents call each other and then they exchange secrets, for instance. And in a way, this is simpler in the sense that secrets are just whatever numbers that they know. And once they have called each other, which this time is only kind of activating one link in the network after the other, so it's kind of an orthogonal perspective. Then there are results on, for instance, how many phone calls do you need for agents to know all the secrets or things like that. But this is not really what you want. In a sense, I would say that the models that I talked about are in an implicit way doing that. So they are not asking questions, but you could consider that networks are announcing their state to their neighbors constantly. Because the typical epistemic assumption behind those models is why do we represent the network? Is because we have this background assumption that agents know the states of their direct neighbor typically, and not the state of other people further away. And they know who are their direct neighbors, but they might not know who are the neighbors' neighbors and so on. And so in this sense, you could consider that this is just one node constantly communicating to its neighbor, something which is pretty much what you do in Facebook posts. So this is still not asking a question, of course, but you could say it's you asking to your neighbors, what is your state today? And then saying, I'm purple, I'm purple, I'm purple. In a sense, that's very basic communication, but I have a feeling this is not what you wanted at all. There's quite a working logic about asking questions, about just the logic of question itself, right? As a partitioning of the state. And I'm sure there would be ways to combine this with that, but I'm again not so sure that I would match what you would want as very simple.
Yeah, there's a sense that asking a question itself conveys information, and I wonder whether how that would be captured in a model. But thanks for the answer. That was really interesting. Think more about it.
Yes, there was a question on the chat, but the person already says, "Nice talk. My question got answered along the way." So so I think we are good on that. And I'm afraid, I hope you don't feel kind of ganged up by the Topos guys, but I also have a question that's a bit similar to Tim's and a bit similar to Brendan's, but it goes in a slightly different way again, which is about, we know that there are other people trying to think about the ways network developed and kind of particular social networks. And, there's lots of work more along the lines of machine learning, especially through the psychologists, at least the ones I know, kind of in Stanford, doing more psychology work. And there's also the work that's more, the work that we know about. I know very little, but I know that Nina Otter, for instance, does some work using more categorical tools. Have you thought about those things at all?
No. No. So the honest answer is no. I don't find this question bad at all, because typically the question is more, why don't you use real data from some specific social network platform, for instance? And the reason is because I'm interested in the general laws, the logical limits of those things. And of course, I'm still making choices and assumptions, so I'm still restricting what I'm looking at, but in a different way than if I would use real data. But So I find your question more fair, actually. But the honest answer is just no, because everybody is somehow working on the same thing using different tools. And about the category side, I have never heard of this, actually. So I'm very curious about this. If you want to send me a...
Well, we can send you the references and stuff, because it's the categorical stuff, because it is. I mean, I'm particularly doing a program in May with Nina is going to be another mentor, and I'm mentoring on some things more to do with computation, and she's mentoring exactly on this idea of social network. So I will learn a bit more. At the moment I'm very incompetent, but you see, the reason I'm asking that, though, and being such a pain in the neck, is because I think the problem I have with all these different methods of modeling things that we're discussing is how do we kind of do this meta level of when is the model a good model? I like very much your models because they speak to me. They kind of deal with the things that I think are essential, like being able to say if it's phi or not phi, and if it's phi, it's not, making this simplifying things to the level of logic that I think is essential. It's very good, but I would like to kind of see if we kind of can have some sort of meta level adequacy proofs of this stuff.
It all depends what one means by adequacy. So this is exactly the issue that I was mentioning before, that most times people want a model that fits one very specific application, and then what you include as possible network structure or possible update rules is completely dictated by this. And in a sense, this is also what we did. What we tried to do throughout all the works I mentioned was to stay as general as possible. So I'm trying to refrain from making assumptions, but I am still obviously making assumptions that things are discrete and they're all synchronic, and there's some level of uniformity, and you can just say, well, any model that is not probabilistic in nature is anyway wrong. You could just stop there, right? So I think it is more interesting than this, in the sense that I once had a discussion with Christian List about this, and he was saying that the difference between those discrete deterministic model and probabilistic models that are much more fine-grained is probably similar to the distinction between classic physics and quantum physics, that if you look close enough, you see more fine-grained things happening, but from a distance, things behave like those very basic models say. And so what we try to do as logicians is just take a textbook about networks. People say those very, very basic threshold models are actually mimicking things that are happening all over the place throughout very different types of network, very different types of attributes, very different type of relationship. And yet they seem to match to some general extent waves of what is happening on network. And this is why I think as logicians, we were attracted to say, okay, we have to pick something to start with. Let's start with what people who worked on models of diffusion for their own sake, what they thought was the most basic components. And of course, because we are logicians, we probably had a preference for some of those things. But at least we tried not to include too many assumptions just to fit one specific detail. But I would agree with you that there is a meta level. For instance, when I meet people from judgment aggregation theory modeling the exact same thing with different tools, then I actually had some students doing projects on comparing the different models and listing what are the different assumptions. Can we translate one model into the other? It's actually quite difficult, because all those subtleties about self-influence and things that are not drawn in the graph but are actually could be translated into graph differences if you take it into another framework. So there are a lot of subtleties there that, but I mean, some people have also said, this is just dynamical systems. I'm like, sure it is, but you have to choose one level of how meta is meta enough. And But I'm definitely open to that discussion because I always like actually that this is a topic that goes through really many different fields. It doesn't have to be logic at all. What I like about logic, of course, is that each of those frameworks contains all the theorems that there is to discover about them, which is a nice feature, but that's the reason really. Otherwise, as a modeling purpose, it's probably not the most handy tool by far.
No, that's great. That's wonderful. I would like to ask if anyone else wants to ask questions now, kind of. Otherwise, I think we should just thank Zoe and kind of stop the recording.
Thank you. I also want to thank you for all the nice questions.
Thank you.
And comments.